Just one second.
That's the on.com. Yeah. Oh, I was pretty good. You know, this I'm on liquid and then stuff. Where were you on Sunday? We had liquid coffee on Sunday. Oh, yeah. Okay, it wasn't like real. It was like 6 months. But you have that covered fault. It's good. And logged in. That's it. I can't see where we can make corners.
You need to upload first.
Oh, to upload first? Okay. You know, and we can just upload whatever we have. Right?
Yeah.
Okay. I'll just upload what we have right now.
Yeah. All right. Hi everyone. So today I want to kind of give you the solution to last week's interview puzzle and give you a new one. Hi everyone. What? So today I want to kind of okay. So last week's interview puzzle, and then we'll do an intro to this week's puzzle. And this would involve basically using loops to solve problems. And that's basically what we're going to be doing for the next while, is just figuring out how, like, here's a problem I want to solve with loops. How do I solve it? So, okay. So with that said, last week's problem was still not really about loops. So if you remember, it was swap the values of A and B without using extra space. And you could do it with extra space by saying, you know, I'll save A in temp, and now that A is saved, I can say A equals B, but the old A is in temp, so now I can say B equals temp. Or I could say something that kind of looks like I'm not using extra space, but really I am, because what this really does is it creates this object that's B comma A, and then it puts it in AB. Really, B comma A is its own thing. We'll do that later on, but that's not allowed. So the idea is kind of like this. So we'll keep track of things. So we'll say, okay, so A currently is containing the original A. I'll name it old A, and B is going to be old B. Hello. And now the hint was you can start with A equals A plus B. So the trick here is to just keep track of things and then do things one bit at a time. So here, what happened is, well, what is now A? Well, A now is old A plus old B. B is still old B, didn't change B. So at this point, if I know that this is kind of the way to approach the problem, I would say, okay, all right, so I just assigned A, so, well, now we need to assign B. What should B be assigned? Well, it should be old A, and I can actually get old A from here, right? So I can say old A plus old B minus old B, that's going to be old A. So that means that I can just say B is equal to A minus B. So now A is still the same. I didn't change it here, but B is now old A because this minus this, that's old A. And well, now you can probably figure it out. So now what's left is to make A be old B. How to do that? Well, it's again, this much minus this much. So that just means that we should say A minus B. And that would make it so that A is now old B and B is old A. And we're done. So would it work? Well, sometimes yes. So with integers, it would just work. You might argue that specifically in Python with integers, we're kind of cheating here because it was supposed to be with no additional storage space. But actually, if A is like 600 and B is 700, then A plus B takes up more digits than either A or B. So that means that A equals A plus B would take up additional storage because you need more digits to store A plus B. And in Python integers, the digits are not fixed, right? So that's why one argument that's like for integers, not really. You could say, okay, what about floats? So if you remember, floats in Python have a fixed number of digits, right? So A plus B, if A is a float and B is a float, A plus B, it's not going to be any different in terms of the number of digits. But if it's not any different, that means that there might be loss of precision, right? So it might be that you need to store a number like 1.0001. How would it happen? Well, if you need 1 plus this kind of deal, well, now you need 1.0001, right? And that might just need more digits in the what's called the mantissa, in the thing that actually stores the numbers. So what would happen with floats? Well, if you can't store this last one, they'll just go away. Python will just round to 1.0, and that's it. So if you do A plus B and A and B are floats, there might be loss of precision in this way. Does this make sense? Questions? So, okay. So, and this is going to be kind of more advanced material, but can you do something with strings? The answer is kind of, right? So you could, first of all, just say, okay, I have like ABC and I have XY. Well, I'll smoosh them together or something, and then I'll figure things out later. That, of course, obviously doesn't count. Like you smoosh two strings together, that takes up more space than any one of the strings individually. So that's not using extra space. You could do something like this. So you could say, okay, I have ABC and then I have XY. So I'll do like ABC plus XY by character. So I'll somehow figure out what's A plus X, and I'll figure out what's B plus Y. And this is just going to be C. And I'll store this instead of ABC. So I'll pretend that the digits are kind of like numbers, which you can. And then I'll do the same trick as before. So that's actually feasible. That's for advanced material. You'll see, like maybe you can try it when you get to ESC190, but that's the basic idea. If you do things like character by character, you can use the same trick. So, okay. So that's that. So I'll first introduce just the interview puzzle that people sometimes give in interviews. I'll then do kind of a straightforward solution, and then I'll leave to you thinking about how would you do it efficiently in a way that would get you the job or something. So first of all, n factorial is just defined like this. So it's like 1 times 2 times 3, and then times n minus 1, and then times n. That's just the definition of what n factorial is. And usually people say 0 factorial and 1 factorial, just 1. So the question is, how many trailing zeros does n factorial have for a given n? So by trailing zeros, I mean something like this. So if you have a number, then this number will have, well, 3, and then so 3, 6, 8 trailing zeros, right? All right, so that's the question. Like, I'm giving you a number like this much, and you're giving me the number of zeros at the end of the number. You might ask, why are there zeros at all after the factorial? But the answer is, like, of course there are, right? Because if you have like 125 factorial, well, you multiply it by 10, and then you multiply it by 11, doesn't matter, but then you multiply it definitely by 20, by 40, and so on. Every time you multiply by something like that, you add a zero. Right? So, okay. So I'll do two things. So first, I'll write the factorial function. Then we'll see. So the way I'll do it, and that's going to be kind of typical of a lot of problems that you'll solve. I'll start with setting the result to 1, and then I'll change the result until I get the right value. So the way I'll do it is I'll say for I in range 1 n plus 1, and I'll multiply the result by I here. So this is the same as result equals result times I, if you remember. And then at the end, I'll return result. So what have I done here? So I said, set result to 1 initially, and then make I be 1, then 2, then 3, then 4, and so on, up to but not including n plus 1, and multiply result by I every time. Right? So initially, result would be 0, and I is nothing, 1, sorry. And then result is 1, I is 1. And then when I is 2, result is going to be 1 times 2. And then when I is 3, result is going to be 2 times 3. And then when I is 4, result is going to be 24. And then when I is 5, it's going to be 24 times 5, which is 120. So 5 factorial, for example, has 1 trailing 0. Right? So several subtleties here, right? So first of all, why did I set results to 1 initially? Well, it had to be something that I would keep multiplying by. If I set it to 0, that would be no good. Why, anyone? So like if I just set result to 0, why is that bad? Yeah. Yeah, exactly. Like I keep multiplying 0 by all the numbers. No point to that because 0 times anything is 0. Right? So instead of starting with 0, it's going to be like 0 times 2, 0 times 3, 0, and so on. So similarly here, I set I to be in range 1 to n plus 1. Why? Well, because I want this. So 1 times 1, I could have done 2 as well. Times 1 doesn't do anything, right? But I do times 1, and then I is 2, and then I is 3, and so on, and I multiply by each of those. So I go up to, but not including n+1 because I want to multiply by n at the end. So it needs to be n+1. Right? And then I return red. So let's try it. So if I'm trying something in the shell, I first do Control-E, Command-E, so that Python reads in the function that I just wrote. If you don't do that, you're going to be using either the old version of factorial, or if it's not there, it's just going to give you an error. So if you want to update, first run Control-E. And now over here, I can say something like factorial 5, and it's going to say 120. That's what we computed before. So I can try something large. So that obviously is going to take a lot of time because it's trying to multiply those huge numbers, right? So I'll interrupt. So this is Control-I, Command-I on the Mac. And I'll do something smaller like 5,000. And you see that factorial 5,000 is like this mess, right? With lots of trailing zeros as well. So something smaller that we can kind of see. So here's factorial 50. Also still a quite large number. All right. So, okay. So we've computed factorial. The other part of the problem was we were trying to see the number of trailing zeros that it had. So how do we compute the number of trailing zeros in the number? So what I'll do is I'll write another function. So how do we do it? So multiple ways actually, but what I want to do here is something that's similar to something that we've done last week when we were doing primality testing, or when we were doing log. It's a little bit like that, a little bit like this. So what I'm going to say is, well, the number of trailing zeros in a number like this, what is it? Well, it's the number of times that I can divide the number by 10 without a remainder, right? So here, 3 trailing zeros. So I can divide by 10 once and divide by 10 another time and divide by 10 another time. Dividing by 10, the same as taking away a 0 graphically. So if I can figure out how many times I can divide the number by 10, that's going to tell me how many zeros there are at the end of the number. So, okay. So what I want to try to do here is to repeatedly divide by 10. I don't know how many times in advance. That's what I'm trying to find out. So that means it's a while loop. Because I want to repeat something, I don't know how many times. So I'll say while. And then when do I want to stop? So I want to stop when the number is not divisible by 10. Not divisible by 10 means k mod 10 is not equal to 0. So that means that I want to keep going. So this is the condition for keeping going while the number is divisible by 10, meaning while k mod 10, the remainder of the division by 10, is equal to 0. This is the same as saying while the last digit of k is 0. Okay, and what do I want to do? Well, I want to divide the number by 10. So I'll say divide equals. And I want to say, okay, I've counted how many is it? I've counted that in. So I'll add a variable, I'll name it counter. Initially, it's going to be 0. And I'll increment counter by 1. So increment just means increase by. And then once I'm done, I'll return counter. So several ways to think about this process. So I think the easiest way to think about the process is to just plug in some number and see if it works. So maybe I'll plug in like 1300. Right? And then initially counter is going to be set to 0. And then, so here I'll do it kind of the way you might do it on the midterm. When you can't run it, you can also trace it, of course, right? So counter is initially a 0, and I'm saying, is k divisible by 10? Well, yes. So divide k by 10 and increment counter by 1. Go back. Is k divisible by 10? Yes. Divide it by 10, increment the counter by 2. Is k divisible by 10? No, 13 is not divisible by 10. We're done. Return counter. We return 2, which is the right thing. We wanted 2 zeros. So running an example like this is always useful. Here's another way of thinking about it that's kind of more, rigorously mathematical. So let's say that I want to prove that trailing zeros returns the number of trailing zeros. Technically, you'll need induction for that, and you haven't done induction yet. So some of you will have done it in high school, but not everyone. But here's the basic idea. So you can say, okay, before we enter the loop, counter is the number of times k was divided by 10, which is 0. Right. And now here, what we're going to do is we're going to say, okay, so what happens inside the loop? Inside the loop is divide k by 10, increment counter by 1 right away. So after an iteration of the loop, counter is the number of times k was divided by 10. So that means that over here, what is true? K is not anymore divisible by 10. Because if it was divisible by 10, we wouldn't be done with the loop. And also counter is the number of times k was divided by 10. Well, if k is not anymore divisible by 10, and also we kept track of how many times we needed to divide it by 10 so as to get it to that state, well, it must be that counter is the answer. That's kind of a proof that the function returns the right thing. Right. So the key here was to say, okay, I'll look before, and I'll make sure that initially counter was set to 0. And sometimes, like, you might mess up and you might say, oh, like before res was equal to 1, because here 1 made sense. So why don't I set counter to 1 here? And the answer is, well, no, counter is supposed to be the number of times that you've already divided the number by 10. And before the loop, you didn't divide it by 10. So it should be 0. And then inside the loop, you just keep track and say, okay, like I updated k, I updated counter. Are they consistent? Well, yes, because I just divided by 10 once. I updated k by 1. And then at the end of the loop, okay, k is not divisible by 10. We made sure that counter contains the number of times that we divided by 10. So it must be the right answer. Okay. So that's kind of a semi-rigorous proof that this works. So I say semi-rigorous because you need induction. Okay, so that's that. So always, of course, try to actually run it. So we kind of ran it in our heads, but let's try to run it. So I'll say trailing zeros, whatever, and it indeed displays 2. So that's great. So now that I wrote the factorial and I wrote the trailing zeros, I can try to combine them, right? So I'll say trailing zeros factorial, and this would be n. And I could just say return trailing zeros factorial event. All right. And it's always good. Like here, there were like really two distinct tasks. So I made two distinct functions for them. Right. It's always good. And I was able to test them individually. So now hopefully there's fewer opportunities for bugs. So now I can ask, okay, so factorial of whatever 500 is this much. So I can ask, okay, so how many zeros is that? And the answer is 124. So, okay. So now this is not going to finish running before the class ends, right? And that's because what I'm doing is quite inefficient. I'm computing the factorial, which is really slow. And then I'm dividing by 10, which is not that slow, to be honest, but still takes some time. So the interview puzzle is not like to come up with this thing. It's to come up with something that would work for a number like whatever, 500, 234, and so on. All right. So think about that. Questions? All right. What's Discord saying? Okay. So, all right. So I want to do another application of loops. So I'll just interrupt this for the thought of its misery. So in the lab last week, you had, actually, you also used the loop. So you had this formula for computing pi, but that was a quite complicated formula. Like probably Davis hasn't told you yet how to derive it. In fact, probably won't. So is there a simpler way to use a computer to compute pi? The answer is yes. But first I want to ask just, okay, like let's say you're on a desert island and you really need to write out pi on the sand so that people will know that there is intelligent life on the desert island or something, but you don't remember what pi is. But you have a measuring stick. How would you figure out what pi is? It's like, you know, like whatever, like how do you figure out like the third digit of pi? Anyone? So one idea would be, well, what's pi? Well, like 2 pi is the circumference of a circle with radius 1, right? So you might just say, well, I'll draw a circle. I'll try to make it good. I'll try to make it so that the radius is 1, then I'll put like a rope around it or something. And then I'll measure the rope, and that's going to tell me what pi is. So I want to do something similar, but with the area rather than circumference. So the idea is kind of like this. So I'll take a quarter circle, and I'll take a square, and let's say this square is 1 by 1, right? So then the area of the quarter circle is 1/4 pi 1 squared, right? Because the whole circle is pi times 1 squared. So the quarter circle is 1/4 pi 1 squared. So pi over 4. The area of the square is, of course, just 1 by 1. And what I'll do now is I'll just, if I do it physically, just throw some sand on this randomly. And then I'll measure how much sand fell inside the quarter circle and how much sand fell outside the quarter circle. And what's going to be the ratio of the sand that fell inside the quarter circle to the overall amount of sand? Well, it's going to be pi over 4 divided by 1. So pi over 4 would be the proportion of descend inside the quarter circle to the overall amount descend that it threw. Make sense? And I could like weigh it or something if I wanted. So how do I do this on the computer? Well, what I can do is I can get some random numbers. So Python provides you with not quite random, but pseudo-random numbers. We'll talk about it a little bit later. So you call a function that's called random.random, and that gives you a random number between 0 and 1. Right? So Leibniz true. Okay. Okay, yeah, not divided by 5. So okay. So random.random is a number between 0 and 1. So I can do multiple assignment and I can say x, y. Didn't have to do it in a one-liner, but I can do like x comma y is random.random, random.random. And what that does, it just puts one random number in x and one random number in y, so that whatever x, y is like this. And then the plan is to generate multiple pairs of coordinates. And count how many of them are inside the quarter circle. So how do you know which one is inside the quarter circle? Well, have a quarter circle here, so this is 1, that's 1. You have a point here, that's x, y. So how do you know if this point, based on the x and the y, how do you know if it's inside the quarter circle anyway? Yeah. Yeah, so the distance to the origin, right? Right, so is smaller than xy, right? So, or like the distance of xy to the origin is smaller than 1, right? So the distance to the origin is square root of x squared plus y squared. So just to make sure that everyone's with me, so this is y, this is x. So just by Pythagoras theorem, this is x squared plus y squared, and this is also the distance to the origin, right? And you can ask, is the distance to the origin smaller than 1? In the same way, you can ask, is x squared plus y squared smaller than 1 squared, which is also, of course, 1. Right, so if it's smaller, then that means that the point is inside the quarter circle. If it's larger, then that means that it's outside the quarter circle. So, okay. So I'll say, okay, so endpoints for a start, let's do 1000, and we'll just repeat. So that's the application of the rule. So we'll make us a random point. It's going to be a new one every time. And then if x squared plus y squared is smaller than 1, then that means that it's inside. So we'll increment by 1. After we're done, we can say, okay, so we have the number of points inside the quarter circle and we have the total number of points endpoints. What's the ratio? The ratio is pi over 4. So inside count divided by endpoints is approximately pi over 4. So that means that 4 times that is approximately pi. So let's try it. So we just compute 4 times inside count divided by endpoints, print it. And of course, you'll get like something slightly different every time, but something that's kind of close to pi. So this is, of course, just for 1,000 points. If we do 1 million points, then we'll get a better approximation. And if we add 10 times as many, we'll get an even better approximation. So here we got like up to 3 digits. If I make it 10 times slower again, we're going to get the weight, and it's not going to be, to be honest, much better. But in principle, you add more points, and the more points you add, the better is the approximation. And all you needed is just random points, right? There's nothing there, and it still kind of approximates pi. So I think that's cool. Yeah. So closer. So now that we did it, we can kind of make it nicer and make it a function. So here we'll return. And that's a common thing. Like at first you kind of mess around, and then once the code is ready, you just say, okay, I'll make it a function, syntax error. And now I can say, okay, approximate pi with, let's say, 50,000 points. And it's that's actually pretty good. But I just got lucky, right? So it's not, yeah, sometimes it's gonna be like this. So this is not as efficient as the Leibniz formula that you were given by a long shot. For kind of the bang for the buck, it's like much smaller. At the same time, it's kind of conceptually nice that you can just say, okay, like, well, it's a circle, so just throw some points in there, look at the ratio, and that's going to be related to pi. All right, questions about this? All right, so one last thing that I want to do today is talk a little bit about break and continue. So some people don't teach those at all because, well, similarly to global variables, those are not considered to be good practice, generally speaking. And it's true, they generally aren't. So we'll talk about better alternatives as I'm teaching. At the same time, 1, sometimes they happen to be useful, and 2, you'll see them in code all the time. So I can't just keep them a secret. So what break does is stop the loop. So for example, you do like I equals 0, and then you say while I is smaller than 1,000, 10,000, whatever. And then you say if I is equal to 123, then break. And here I'll just do print I. So what's going to happen? I forgot I plus equals 1. So what's going to happen is we'll stop at 123, right? So we first add, then print. So that's why the first thing that's going to be get printed is 1 here, right? Because I is 0, and then I plus equals 1, and then print I. So the first thing that gets printed is 1. And then the last thing that gets printed is 123, because when I is equal to 123, right after you printed 123, then it checks, is I equal to 123? If yes, break. So it gets out of the loop, right? Now, is this a good idea in this case? Well, clearly no. You could write better code here, right? So you could say something like, well, if you want to stop at 123, just stop at 123. So you could say, while I is smaller than 123, just do this. So this is cleaner and clearer. So continue is stop the iteration and go to the next one. So again, we could go here. So 123 is kind of large, but I'll say like while I is smaller than 10, and I'll say if I is equal to 5, then I'll continue. And otherwise I'll print. So sorry, not 5. Yeah, 5 is good. 1. It's 1. Oh yeah, so here it's a problem. So I plus equals 1 should be here. The other situation was actually kind of interesting, but we'll talk about it later. So this is like this. And what happened is I printed 1, then 2, then 3, then 4. And then here it says if I equals 5, then continue. So that means that when I was equal to 5, I didn't get to print I switched to the next iteration and then printed 6. Make sense? So again, should I do this kind of thing? Well, here you might make a case for it. You might say, okay, like 5 is like an exception. So let's just handle the exception like this, where if you have an exception, just don't print it, don't do anything, just go to the next iteration. More often what you would see is something that's kind of like this. So it would be if I is an even number, then continue. And if not, then print. So that would print something like 1379, right? And that's because every time it's an even number, we just say continue, so we don't print because we never get to print I. If it's odd, then we get to print I and we print it. Well, if you want something like this, several options that you have that are better, right? So one thing you could say is, okay, all right, so you only want to print odd numbers. Okay, sure, just print odd numbers. So just say if I mod 2 is equal to 1, then print. That's the same, but much cleaner. You could go even further and say, okay, if you want to print just the odd numbers, there is a way to just go through the odd numbers. So why don't you do that, right? So why don't you, instead of doing something like this, you just say I plus equals 2 and start from I equals 1, and then you can just say print I. Right, so that's again the same, where you start from 1, and then you again go up to 10, but not including 10. And then you just go from 1 to 3 to 5 and so on. You don't need the if statements because you're incrementing time by 2 every time. And most of the time, rather than do break, you probably want to do something like that. Or rather than to continue, you probably want to just rethink the condition in the loop. Sometimes there are exceptions. Most time, if you're tempted to use break or continue, it's an indication that either you want to rewrite the conditions over here, or you want to rewrite something like this, or maybe you want to help a function which would have a return rather than a break. That's usually better practice. So you'll see more examples of this kind of thing later on. Right? Questions about anything? No? Questions on Discord? Seemingly no. All right, I'll see you Wednesday. Thanks. Oh, you have a question.
For while it's generally before the block of code or after the block?
I mean, that depends on what you want to do. Like usually you would see after more easily than before. The reason I didn't want to do it is because we have it continue and the increment is after, then you get into so yeah. All right, I'll see you Wednesday. Thanks. Bye.